Alright guys, sorry about that, video cut out. So now we got to just quick talk about the individual forms of energy and a little bit of conservation of energy. So this is a big chapter in the book, but they don't ask so many questions in the regions, unfortunately. Alright, so we have kinetic energy, 1/2 mv squared. Gravitational potential energy, mgh, and spring potential energy, 1/2 kx squared. Now, when we're going through these and talking about these forms of energy, you know, remember the bar diagrams, right? So like classic, a car starts at the top, right? Goes down, rolls across the bottom, right? Rolls across the floor. So we look at the energy bar diagram. So PEG, PES, KE, PEG, PES, KE, and then E internal. All right, so check this out. Remember, if there's not literally a spring or rubber band in the drawing or the setup, there's no spring potential energy. So initially, let's say it starts off with all gravitational. At the bottom, it would be all kinetic. So the PEG at the top equals the KE at the bottom. All right, so you'd say mgh at the top equals 1/2 mv squared at the bottom, and solve for whatever it is you need to solve for. Either you know how fast it's moving at the bottom, and you want to know how high it started, so you'd solve for h. Or you know the height it was dropped from, you want to know the speed at the bottom, you solve for v. Now, sometimes you say, okay, 20% of the energy, let's say, is built up to thermal energy. All right, let's say internal energy takes 20% of it. Well, that means of our initial energy, we only have, that's what happens when I forget to lock the focus. I only have 80% of my initial energy that can become kinetic. So you don't see that question too often on the Regents, but I think it's a really worthwhile question to ask, because we're always dealing with energy efficiency, right? That's something that is very important in modern society. Make sure things are energy efficient, right, to prevent unnecessary release of greenhouse gases and thermal energy, right? The more efficient things are, the better it is for everybody. So anyway, that's what we do. Gravitational energy into kinetic. Now, it could be a spring. It could have been a spring launching this thing on a flat ground, right? So we just keep modifying these. It'd be all spring potential energy. So now over here, it's not PEG, it's PES, and it's 1/2 kx squared equals 1/2 mv squared. So maybe you have to find the spring constant, maybe you have to find the velocity, who knows? Conservation of energy, very powerful, very important, wonderful topic. Let's see, they dedicate a whole thing to elastic potential energy, F equals kx, good old Hooke's law. That's where you got to be careful sometimes. This is spring energy, this is spring force, right? Force. Newtons per meter is K, X is meters, the meters canceled, gives you newtons. Over here, you got newtons per meter times meters squared, so one of the meters cancels out, and you're left with Newton meters. That's joules. So this is spring potential energy, this is spring force. Hooke's law, spring potential energy. Don't forget about that. Some good questions in there. I don't have the answer key posted for this topic. I'll do that today. I'll have to scan it and get this posted up there. One last thing to talk about really quick is the concept of total energy and mechanical energy. It's important to realize that in a system, the mechanical energy is simply just the sum of the kinetics and the potentials. And this could be both PEG and PE spring, or one or the other. All right. So E total, ET, it's everything. It's PE, KE, it's heat, which they call Q, which is dumb, E internal, thermal energy. This is what's conserved. Total energy is conserved. Always. All right? Total energy conserved, because this could also be an input energy, right? right? Some sort of input work on the system. You know, you keep track of totally all the energy. All energy is always conserved. However, mechanical energy is not conserved. So when we're talking about energy efficiencies, you know, we want to maximize the conservation of mechanical energy, right? Because we don't want stuff flowing out of the system being lost. We want to keep it in, but you know, that's the inefficiency. The inefficiency is the energy that's leaving the system in the form of heat, typically heat, right? That's the big spoiler of energy conservation, of thermal energy. You know, so that's one of the big advantages of hybrid electric cars is they can use the motor to stop the car, brakes, and actually in doing so, you take that kinetic energy that you're taking out of the car and it actually goes back into charging the battery, which is so cool. I love it. Regenerative braking, I think it's called. But anyhow, that's the key there is mechanical energy is just the sum of the kinetic and potential. Total is everything. Total is what's conserved. Mechanical energy is not necessarily conserved in a setup because energy can leave the system in terms of thermal energy. So sometimes we get these problems where we determine the initial energy we have, and we have 200 joules, but then when we see the object moving, we say, wait a minute, that's only moving with 100 joules of energy. Where'd the 100 go? Well, it went into thermal energy somehow. Be it air resistance, that's going to cause things to heat up. We see that with the re-entry of space probes, right? That friction from the air causes them to get very hot. So air resistance is friction, essentially, and it causes the object to get warm. That's internal energy, so you lose mechanical energy. Anyhow, I got to leave it there for now. I've been blabbing on at you. Love you all. Be good out there. Be safe. Talk to you later.